So today's lesson is going to focus on energy and how energy is never created or destroyed, but that it can change forms. And that ability for energy to change forms is how we get electricity. At all types of power plants, we take some sort of fuel source or some type of movement and we transform that energy into electrical energy, which is a type of potential energy. So the lesson is going to focus on potential, the difference between potential and kinetic energy. Potential obviously being stored energy, energy that's ready to be used. Kinetic, that's energy that's not really being used up, because energy can't be created or destroyed, but it's the energy of motion, of sound, of heat. But it's not being destroyed, because all the energy in the universe has always been in the universe. It's never created, never destroyed. And we're going to focus today on the idea of hydroelectric power. How do we get electricity from flowing water? And students are going to be building their own model water wheels today. And the goal is to see how many times you can get your water wheel to rotate. Obviously, the more times you can get something to rotate, the more energy it will produce. Now, I have to give credit for this lesson, first of all, to the Integrated Teaching and Learning Program at the University of Colorado at Boulder. Specifically, I think it comes from the engineering department. And I found the idea for this lesson originally on a website called teachengineering.org, which is another just a fantastic resource. If you haven't seen that, I'd encourage you to check it out. All right, so that said, our standard today is 8.2.2, identify and describe how energy systems and matter interact. So I think I'm just going to get right into this lesson, how I want students to work through this and what you'll need for them to do this activity. So the first thing they're going to need is a couple of bottles that are similar size, and I've already cut the bottoms off of mine, and that's the first step, is cutting the bottles so that they're going to fit together to make the body of the water wheel, the water turbine. And I didn't cut mine exactly straight, so when I go to tape them, I need to be careful to make sure to tape them, so that the openings are straight across from one another. That's going to make a difference how they spin, obviously. If they're really crooked, it's not going to work very well. And so students will take their bottles and they're going to put duct tape right here around the middle to hold these together. All right? And that'll be the body of their turbine, and then they're going to be using note cards to create the fins for their turbine. Now, they can have as many as they want. They can have, 20, whatever, however many they can fit on there. And the advice I always give to students is to think about falling water, hitting this, and think about how you're going to make this fin stiff enough so that when the water hits it, it doesn't just fold right over. Because that's going to be important. You want this thing to continue to spin as many times as possible. So once the students get their turbines built, which usually takes 15 or 20 minutes, right? After they get them built, we'll use a testing apparatus I've got set up to test and see how many times their turbines go around. So I have a completed turbine here. It's a 4-fin one. It's a little beat up. It's been used quite a few times, but you get the basic idea of the design. And I'm going to move this over here to the testing site and show you how that works. Okay, so here's the testing site, and all it is a tote with a wooden dowel across it, a 1/2-inch wooden dowel, and I've got it taped on one end here so that we can lift up, and we'll put the turbines on the dowel so that they can now spin freely. And basically what we're going to do, okay, is to find out how many times these things go around, we're going to use this yarn or this thread over here. And so the students will put theirs on, and then you'll just take the thread and put it right here at the neck of the bottle, and take a small piece of tape, and that tape is going to go right here to tape that thread onto the bottle. Now, when the turbine spins, okay, the thread wraps around the neck of the bottle. And we'll be able to use how much thread is on the neck of the bottle to calculate how many times the turbine went around. I always like to let students pour the water because the rate of flow obviously is going to make a difference. Okay? So I usually give them about 1/2 gallon and let them pour, and one person kind of watches the string, make sure the string stays around the neck, and they just get to continue to pour as many, as much as quick as they want or as slow as they want. And, okay. So when they run out of water, that's it. What we'll do is we'll just cut the string at the neck of the bottle. Okay, they'll take their turbine off, kind of shake it out, and now they've got this length of string. Okay, and I'll ask students to tell me, how can we take this length of string now and calculate how many times your turbine spun around? And the obvious answer is we have to know the circumference of the neck of the bottle, and we're going to find that circumference, and then we'll measure the string and divide by the circumference. That'll tell us how many times it went around. So if I have 100 centimeters of string, and the circumference of my bottle is 10 centimeters, I know my bottle spun around 10 times. So I get a wide variety of numbers of rotations. I've had anywhere from 1 or 2, sometimes none, if it's a really poor design, up to as many as 37 times around with half a gallon of water. So the design definitely makes a big difference. So here's a kind of a demonstration I like to add sometimes if I have time when I'm talking to students about energy transferring from one form to another as we move towards electricity from water. You start with the gravitational potential energy of water, and that then you get this falling water that hits the turbine and gets transferred to mechanical energy of the spinning turbine, which is then transferred to electrical energy. As the turbine spins, right, it produces electrical energy because of the electromagnet inside of it, and you end up then with electricity, which can then be used to run all kinds of things, light, heat, your computer at home, whatever. And what I like to ask students is, why bother building a dam? I show them a picture of Hoover Dam and just ask them, why go through all the trouble of that? I mean, it seems like a lot of work. Why not just stick the turbine right into the river? And of course the answer is, the higher we can get the water off the ground, the more potential energy we start with. And since we're going from one form of energy to another, the more energy we start with at the beginning, the more potential energy we start with, the more we're going to end up with in the end, the more electricity we have. So the higher the water is off the ground, the farther it has to fall, the more speed it's going to pick up, the more work it's going to be able to do when it hits the turbine. And so I like to sometimes do a demonstration with 3 pop cans if they're having trouble getting it, which most classes do have a little bit of trouble thinking of why exactly we would build a dam. So I start by showing them a science textbook, and really is no good except for dropping on top of cans anyway, so let's use it. And I'll start by holding the book really close to the first can and asking what will happen if I drop a book on a can from this height. And nothing will happen, so you drop it, and basically nothing happens to the can. Alright, what if I hold it a little bit higher? What's going to happen to the can? Well, it'll probably be crushed a little more, so you do that. And you can show kids, you get more energy because the book was higher off the ground. It's going to have a greater distance to fall, pick up more speed, and hit the can with more force and do more work. And then of course the third one, you hold it way up as high as you can over your head, if you can hit it still and drop it, and show that it does a lot more work. It really crushes the can. And then ask them again, alright, why do we have it? Why do we dam a river? And then almost always kids get it. Oh, if you start with the water higher off the ground, you're going to get more energy, right? More energy from that water, and so you can end up with more electricity. So that's a good demonstration, I think, to add to this lesson. It helps make it more concrete, this idea of energy transfer and how energy is not created or destroyed. And so if we start with more, we're going to be able to end up with more. All right, so to kind of close the lesson down, I also have a worksheet that students can do. It's got a math extension. Kind of it lets them think a little bit more about how energy is produced from a water turbine. I have them do a kind of a simple, but it's really made up calculation. I just assign a number of kilowatts to each rotation of their turbine, and they use that information to figure out, okay, how many houses could their turbine power, and how much would it cost compared to other types of electricity and things like that. And so you can find that worksheet right below this video. But again, the take-home lesson on this is the idea of energy conservation. Energy cannot be created or destroyed. It just changes form from one to another. So when we produce electricity at a power plant, we are not creating energy. We're just taking energy from one less usable form, fossil fuels, or in this case, falling water, and transferring that energy to a much more usable form, electricity. Really fun one for students, and I think everyone will have a lot of fun. It does get a little messy, so you might want to have some towels ready because sometimes it can get a little wet. But that's all part of the fun. Okay, we'll see you next time.